Good morning, everyone. This is July 25th, 2020. We have Able Leadership class, Express Education today, and it's live on YouTube as well. First, I want to welcome our high school leader. Sam is here. Sam, can you please introduce yourself first and then introduce today's teachers and today's subject?
Okay. So hi guys, I'm Express Education's president and also Able Leadership's president. So for today's class, the first half will be will be taught by Kashyap and Jonathan. They'll be teaching you guys about chemistry following the last session that they did, and the second half will be taught by Elizabeth and Michelle. They'll be doing their second part on English, also according to last time. So I'll be giving today's lesson to Kashyap and Jonathan. So just take the lead.
Okay, so for today's lesson, we're going to be going over atoms and ions. So start with a bit of reflection from last week. We went over valence electrons, and to just quickly go over that, you take the element fluorine. Fluorine in the periodic table of elements is in group 17 or 7, which means it'll have 7 valence electrons, and valence electrons are the electrons in the outer shell. So as we see here in this outer shell, which is 2, there are 7 electrons orbiting. And why are valence electrons important? It's because that in every group, all the elements in the same group have similar properties. So all the elements in group 1 would all have the similar properties, that they're really reactive and they're metals, and just like for group 7, 6, and all of them. So next we also went over metals, non-metals, and metalloids. As you can see, metals are on the left of the periodic table, while most of the non-metals are on the right. And the metalloids kind of split the metals and non-metals and have properties of both metals and non-metals. The metals would be like good conductors, they're not brittle, they can bend, but then non-metals would be brittle and often are more gaseous. Okay, so let's start with the atom. The atom is the basic unit of an element that holds the properties of an element. Now, what does this mean? If you take an element and break it down into smaller pieces, you'll keep on getting smaller pieces until you get an atom, and that atom is still part of the element. So if you take carbon and break it down into millions of pieces, and you find a singular carbon atom, that singular carbon atom is still carbon. Now, if you break that atom into further smaller pieces, it will no longer be in carbon. So that's what it means to be an atom. It still holds the properties of the element. So next we have the proton. The proton is part of the atom, and it's in the nucleus of the atom. So as we could see here, this is the nucleus, and there are 1, 2, 3, 4, 5, 6 protons, which means this is a carbon. So this is in the nucleus, and then we got the electrons orbiting around the nucleus. And why is the amount of protons important? It's because the number of protons in an element is the atomic number of that element. So if we go to the periodic table of elements, above each element symbol, there's a number. For hydrogen, it's 1, lithium 3, beryllium 4, boron 5. And this number is the atomic number. And it tells us how many protons are in that element. So carbon would have 6. And as we can see here, there are 6 protons in this nucleus, which means this is a carbon atom. And protons also have a positive charge. Next are neutrons. Neutrons are also part of the nucleus. They don't have any charge, and unlike protons, with protons, if there are 6 protons, that means it's carbon. But a carbon atom does not need to have 6 neutrons. It can have 7 neutrons or 5 neutrons and still be a carbon atom. So let's go to electrons next. If it's a bit confusing now, it'll all make sense in the next couple of slides. We're gonna go over all of them together. So electrons have a negative charge, and they orbit around the nucleus, which is composed of neutrons and protons. And they have a negative charge. So if the protons have a positive charge and the electrons have a negative charge, that's what attracts the electrons to the nucleus and why they orbit around the nucleus, because opposites attract. And also, like neutrons, electrons can differ in the amount of electrons they are. A carbon atom doesn't need to have 6 electrons. It can have 7 or 5. But a carbon atom must have 6 protons. That's a must. So, any questions so far? If you guys have any questions, just feel free to ask in the chat if you don't want to speak. Okay, no questions. Then I'll ask this question. So based on this periodic table of elements, as you can see here, silicon. How many protons will a silicon atom have, based on what you see in this periodic table? Can anyone tell me how many protons are in this silicon atom?
14.
Yep, that's right. So that's good. Okay, next is atomic mass unit. An atomic mass unit is approximately equivalent to the number of protons and neutrons in an atom. So the nucleus is composed of protons and neutrons. And atomic mass unit is roughly the number of protons and neutrons in an atom. Now, the 1 AMU is roughly equivalent to this really small number here, but in more simpler terms, we would just consider a proton to be 1 AMU and a neutron to be 1 AMU, because they're roughly this mass. And the mass of an electron is so much smaller than a proton or a neutron, which is why it is not really taken into the atomic mass. When we're talking about an atom and we want to know what is its mass, we don't take in the electron. So what does this mean? So as you can see in this picture, we have carbon 12 and carbon 14. Now why is there a number after carbon? Well, the 12 means how many protons and neutrons are in this atom. We have 6 protons, which are the plus symbol, and 6 neutrons as well. So if you add up 6 and 6, you get 12. So carbon 12, which means there are 12 protons and neutrons in the nucleus, and it weighs 12 atomic mass units. Now we have carbon 14. Carbon 14 has 8 neutrons, but it still will always have 6 protons to still be carbon. So it can differ in the amount of neutrons. And it has 8 here, and if we add 6 and 8, we get carbon 14. So carbon 12, carbon 14, there's also carbon 13, and other carbons are all called isotopes because they vary in the number of neutrons that they have. So as in this image, we see average atomic mass, and the average atomic mass is the weighted average of the different isotopes. So carbon 12 weighs 12 atomic mass units, carbon 13, 13, and carbon 14, 14 atomic mass units. Now, in Earth today, 98.9% or 99% of all carbon is carbon 12, while only 1% is carbon 13 and carbon 14 even less than that. So if you take 99% of 12 and then you add that to 1.1% of 13, so basically if you multiply 12 by 0.99 and multiply 13 by 0.01, because you're taking the percentage, you would get the weighted average. And the weighted average, you might not be able to see this, but carbon's weighted average, average atomic mass, is 12.01. So 12.01 you would get from multiplying 12 by 0.99 and 13 by 0.01. Adding that together, you would get around 12.01. So that's the average atomic mass. So a question. How many, can someone tell me the average atomic mass of iron from this periodic table?
$26.
This is Hilbert.
Oh, this is
Hilbert says 26.
Are you sure? Iron.
I mean 8.
So 26, you got this number right here, right? 26 is the atomic number. It tells you how many protons are in iron. But if you want the average atomic mass, you would get this number right below iron. That's 55.845. So 55 is the average atomic mass, and 26 is the number of protons in every iron atom. So for copper, there are 29 protons, and the average atomic mass is 63. For calcium, the number of protons are 20, and the average atomic mass is 40. Now, as we can see here, usually the average atomic mass is double the number of protons, because what the average atomic mass is usually the number of protons and neutrons in an atom. Now, if you have 20 protons and you have 20 neutrons, you get 40, right? So this is telling us that most calcium atoms have 20 neutrons plus the 20 protons that it needs to have to be considered calcium. All right, next we have Avogadro's number. And Avogadro's number is 6.02 times 10 to the 22. Now, this might not make much sense. Basically what it's saying is that if you take the average atomic mass and multiply it by this large number here, you would get 6.94 grams, or in lithium's case, 6.94 grams of that element. So if you take lithium's average atomic mass, which is 6.94, and multiply it by this number, this big number right here, you would get 6.94 grams of lithium. And what is Avogadro's number? It's basically the number of atoms. It's a number of atoms. So if you take 6.02 times 10 to the 22 atoms of lithium, you would get 6.94 grams of lithium. So if to kind of represent how small an atom is, if you take the strand, a strand of your hair, and you go to and you don't measure by length, but you measure it by width, there would be like millions of atoms across that length. So that's why this number is so huge. Okay, so next is the mole. The mole is Avogadro's number, but not in number form. So we would say 1 dozen is 12. And for a mole would be 6.02 times 10 to the 22. So a mole is Avogadro's number. And if we take a mole of atoms, let's say a mole of lithium, we would end up with 6.94 grams, which is the atomic mass. If we take a mole of boron, we would end up with 10.81 grams of boron. So can anyone tell me, if we take a mole of carbon, how much carbon in grams will we end up with? If anyone has any questions, they can ask me. Or say it in the chat. So the question was, if you take a mole of carbon, how many grams of carbon would you get? So it would be 12.01 grams, because as you can see, the average atomic mass of carbon is 12.01. So you may be confused about average atomic mass and the mole. So I'll try to explain a little bit better. So going back to average atomic mass unit. So one proton or one neutron is one atomic mass unit. So if we take carbon here, this is a carbon atom because it has 6 protons and it also has 6 neutrons. So 6 plus 6 is 12. And since electrons barely have any mass to where they're basically discounted, this carbon atom weighs 12 atomic mass units. And that atom would be carbon 12 because it has 6 protons, 6 neutrons, 12 atomic mass units. But if we add 2 more neutrons, it would make carbon 14. So carbon 14 weighs 14 atomic mass units. Now, going into Avogadro's number, if you take 6.02 times 10 to the 22 atoms of carbon 12. Carbon 12 weighs 12 atomic mass units, right? You take 6.02 times 10 to the 22, which is like a super big number of atoms of carbon 12. You would get 12 grams of carbon as a result. 12 grams of carbon is also really small, but it would take 6.02 times 10 to the 22 atoms of carbon 12 to get that many grams of carbon. So this is another kind of image showing you the different types of hydrogen in this case, because hydrogen has 1 proton always. Now there's protium, deuterium, and tritium. They're all isotopes because they differ in the number of neutrons. They're all isotopes of hydrogen. Now this notation is called a nuclear symbol. And the number on the bottom tells us the number of protons in hydrogen, which is 1. And the number on the top tells us the atomic mass units of this particular protium. As you can see, we only have 1 proton in the nucleus, which is why the atomic mass of protium is also only 1. Now if we go to deuterium, there's a proton and a neutron. So there's 2 atomic mass units. Tritium, 3, because there are 2 neutrons and 1 proton. Let's go to ions now. An ion. Now, a neutral atom has the same number of protons and electrons, right? If you have 6 protons, 6 electrons, they cancel out. That would be considered a neutral atom because protons are positive and electrons are negative. But what if there was a different number of electrons? Then that atom would be considered an ion. So this image has Cl. This stands for chlorine. So the chlorine element. Now there's a negative next to chlorine, and that's because this chlorine atom has 1 more electron than proton. So if we go to we pull up the periodic table of elements, and we go to chlorine, we see here that chlorine has 17 protons, because that's the atomic number on the top. Now, that chlorine had a negative beside it, which means that it had 1 more electron than proton. So that chlorine atom would have 18 electrons instead of 17. Now, if it did have 17 electrons, it would be considered neutral because there are 17 protons and 17 electrons. So again, talking about the nuclear symbol, the number on the bottom is the atomic number, which is the number of protons in boron, and that's consistent for all borons. But the mass number is the number of protons and neutrons, and in this case, there would be 6 neutrons, because if boron always has 5 protons, to get an atomic mass of 11, we would need 6 neutrons. So 5 plus 6 would be 11. Now we have this charge here, which is -3, or -3. And this means that there are 3 more electrons than protons. If this boron atom has 5 protons, then it would need to have 8 electrons. So this boron has 8 electrons because it has a -3 charge. Now you might be wondering, this has 1 plus. So what does this mean? This means that this sodium ion has 1 more proton than electron, so it has less electrons. So as you can see here, sodium has 11 protons. It has 12 neutrons because 11 plus 12 equals 23, which is what we see here, which is the mass. And the number of electrons is 10 because we see +1 here. And that means that it has 1 more proton than electrons. So this is an overall image of what we learned today. Now, a final question before Jonathan's going to talk about compounds. is if I take carbon 13, if I have an atom of carbon 13, how many neutrons does carbon 13 have? Can anyone tell me how many neutrons would carbon 13 have? So carbon has 6 protons. 13 represents the atomic mass. How many neutrons would carbon 13 have?
7?
Yeah, that's right. Good job. So it would need 7, right? Because 6 plus 7 is 13. So it's just basic maths. The concept might be confusing, but once you get it, it's just basic maths. So that's it for me. I'm gonna stop share. Alright, Jonathan, you can share your screen now.
Okay, so today let's first talk about physical change and chemical change. So the definition of physical change is physical changes are changes affecting the form of a chemical substance, but not its chemical composition. No new substance forms. For example, melting, freezing, and evaporating. Here's a more specific example for physical change. From ice to liquid water, the form changes from solid to liquid, but is still water. From liquid water to water vapor, the form changes from liquid to gas, but is still water. So the key to physical change is that the form of the substance changes, but the chemical composition will stay the same, and there will be no new substance created. So here comes some more examples. Can anyone tell me, is breaking a pencil physical change?
No,
Can you tell me why?
because it's still in the same form except it's broken up.
Yeah, it's still the same substance, and even though it is broken, no new substance forms. So it is physical change. Because the key to judge is a physical change or not is that if there will be new substance forms. In this case, you break a pencil, it won't create any new substance. So it's physical change. Did I explain explicitly?
I don't get it.
So basically, when you break a pencil, right, you won't create any new substance. The pencil is still the pencil, even though it is broken. Did you get it? Let's see more examples. See if you can get better understanding on that. So it is cooling and heating an ice cream physical change. This one, cooling and heating an ice cream. Is it physical change?
Yes.
Yes. Yeah. Yeah. It is physical change because even no matter you cool it or heat it, the ice cream is still the ice cream. The solid or liquid are both ice cream. You don't create any new substance. Like from ice to liquid water is the same thing. The form changes from solid to liquid, but it's still water. In this case, it's still ice cream, so it's physical change. How about lighting up? How about lighting up a light bulb? Is it a physical change? This is kind of tricky.
Yes, it is.
Yeah, it is physical change because when you light up, even though it lights up, there's no new substance created. It is just the light bulb that has been lighted. No new substance created, so it's physical change. How about charging? Charging a phone.
No, it's not a physical change.
Yeah, I agree because there's a new substance coming in.
Yeah, right. Exactly. This is not physical change because there's new substance coming in. They fill the battery. Yeah, so it seems like you get a very good understanding of physical change. Let's move on to chemical change. So chemical change is basically the opposite, the opposite of physical change. The chemical composition changes and new substance is formed. So basically, charging is chemical change because there's new substance formed and fill the battery. And another example, water decomposes to hydrogen and oxygen. The chemical composition of water changes. There are two new substances formed, which is hydrogen and oxygen. So it's chemical change. And more examples for chemical change are burning, decomposition, and any other reactions that can create new substances. Okay, so we have a very interesting experiment below, which is called flame test. The key to flame test is that when burning different metal ions, different colors are produced. It is very cool. Let's watch it.
Jonathan, the voice, the sound is not there. You need to turn on the computer sound. Do you know how to do that? You just look for the place, have three dots, and then you turn on the computer sound something.
Turn on the computer sound.
Yeah.
Jonathan, so there's like a arrow right next to your share screen. So when you open that, there'll be like multiple windows, and at the bottom left, there's going to be a checkbox saying that enable audio for share screen. Yeah, you have to check that box.
Is it more?
So there's an arrow right next to your share screen. So press on share screen, and then there's going to be like multiple windows. Select the screen that you're sharing. Go to the bottom left. There's going to be a enable computer audio for share screen. Check that box, and it should work.
Okay, yeah. I still kind of
So just look at your screen. There's a place that share screen. There is a button, and there is a arrow, little arrow. Click into that arrow. Did you find share screen?
Okay, I'll find it out later. But for the experiments, we don't need to.
Oh, you don't need to listen the sound.
Yeah,
Okay.
yeah. Right.
Okay, can you play again, just from beginning?
Okay, yeah. It's actually not very important from the beginning, but we can play again. It's just a procedure of the experiments.
Jonathan, you can just explain what he's talking.
Yeah, we can actually just see the flame test. Yeah, we just see the flame test. Neglect the procedure.
Lights are down. I've got a meter rule with a splint attached. My audience are 3 meters away.
Okay, so anyone can so everyone can see the video, right? Just even though you can't listen to the sound, you can see the video, right? You can see the different colors of flame, right?
Yes.
Okay, yeah, that's good. That's good enough. So what color did you see in the experiment? Okay, for example, I see green and red. Do you see any other colors?
I saw a lot of different colors like red, green, and blue and yellow.
Yeah, that's basically all of them. Another question. Do you think flame test is physical change or chemical change?
Chemical change because they added a substance which formed a new substance.
So actually is physical change. Yeah, when I first made this question, I also think it's chemical change, but let's explain why it's physical change. So there's some difference between general burning and a flame test. In general burning, oxygen takes part in, and a new substance is created, like water and the carbon dioxide. But in flame test, you add something into the beaker, but you don't create anything. And when you ignite them, when the flame presents, the flame is not the same as this flame. In this case, oxygen doesn't react with the metals in the beaker. So the principle of flame test is basically when you heat the metal ions up, the metal ions emit a specific color in the form of flame. So in flame test, no new substance is formed. I know it's kind of confusing. If does anybody have any questions? Okay, so just reiterate. In flame test, the flame is not the same as the general burning. The flame is just a form for the metal ion to emit a color in terms of flame. So actually, there's no reaction happening there, and no substance is formed. So it's physical change. Okay, but this is very interesting. The flame test is very colorful. Okay, so there are some more examples. We already talked about the general burning, which is chemical change, right? So how about firework? Is firework chemical change?
Yes.
Because it produces oxygen. I mean, not oxygen, carbon dioxide. Like you could see the smoke when you fire it.
I think so. Basically, is the principle of firework is flame test, which makes it physical change. But there are some other substance that react, which makes it chemical change. So yes, it is chemical change. So how about lightning? Is lightning chemical change?
Yes.
So basically, what kind of new substance do you think it will produce?
Lightning.
It will produce heat and I guess.
Yeah, but heat is not a substance. Heat is energy.
Doesn't it produce lightning?
So yeah, but it's just energy. It's not substance. So basically, lightning is physical change because there's no new substance. Even though it produces light or heat, but light and heat are not substance. They're energy. Okay. Did you get it?
Yes.
Okay. How about orange goes bad? Is it chemical change?
Physical.
I think it's chemical.
Right. What kind of new substance do you think it produced?
It produced it makes the mold grow, which is new.
Yeah, right. Yeah, that's right. So, yeah, that is physical and chemical change. A little conclusion is that physical change is no new substance forms. chemical changes, new substance forms. Okay, so let's move on to compounds. The definition of compounds is substance composed of two or more elements in fixed proportions, can be separated into similar substances and elements only by chemical methods. For example, water. Water comprises two elements, hydrogen and oxygen. The formula is hydrogen to oxygen, which means the ratio of hydrogen to oxygen is 2 to 1. It can be separated into hydrogen and oxygen by chemical method. So you can see the substance composed of hydrogen and oxygen, which is two elements, in fixed proportions, which is 2 to 1. And it can be separated into similar substance like hydrogen and oxygen. So water is a very good example of compounds. And we have two kinds of compounds, which is ionic compounds and covalent compounds. Let's see ionic compounds first. Ionic compounds is a chemical compound composed of ions held together by electrostatic forces termed ionic bonding. For example, sodium chloride. We have just discussed ions, so this should be easier. Sodium chloride contains composed of sodium ion and a chloride ion. Metal tends to lose electrons, non-metal tends to gain electrons. That's why sodium loses one electron, which makes it has one more proton than electron, so it has one positive charge. For chloride, it gains one electron, which makes it have one more electron than proton, so it has one negative charge. And a positive charge and negative charge attract each other, which is called ionic bonding. And sodium chloride is formed. Does anyone have questions here? So, okay, so do not be intimidated by the fancy term ionic bonding. It is just positive and negative attract each other. It is very simple. And this is the principle how ionic compounds form. So if no one have any question, we can see some more examples of ionic compounds. Here's sodium chloride. Here's silver iodide, which is yellow. Here is manganese sulfate, which is kind of green and blue. And we notice that the melting point are all very high, above 1000. So here comes some properties of ionic compounds. High melting point and boiling point always have metal. Some are soluble, some are not. And some are white, some present colors. In structure, the ions pack together through ionic bond. So here is a structure of sodium chloride. The purple circle is sodium. The green big circle is chloride. You can see the sodium ion and the chloride ion packed so closely. And this structure extends in three-dimensional space, which forms this kind of structure. You can see these are all kind of like cubic shape, right? And this is the structure of salt we see and we use every day. Okay, so this is the general understanding for ionic compounds. Let's move on to covalent compounds. Covalent compounds composed of two or more non-metal elements, and the metal is not present in covalent compounds. Let's see some examples of covalent compounds. There's water, carbon dioxide, and glucose. So we can see there are some little particles composed of several circles, right? And we call this little particle molecule. Unlike the structure of the ionic compounds, which pack so closely, the structure of covalent compounds is composed of thousands of little molecules. And the distance between the molecules is relatively far. And in this case, it is a very big molecule composed of more atoms than the two before. But it is also a molecule. It's just a bigger molecule than the first two. The first two molecules only contains 3 atoms, but this contains of 24 atoms. But it's still a bigger molecule. It is still a molecule. And we can see the boiling point of the covalent compounds varies very differently. For water, the boiling point is 200. For carbon dioxide is -100. For glucose is over 1000. So covalent compounds can be gas, liquid, or water. Does anyone have any questions here? Okay. So I'm also going to introduce a new term called covalent bonding. So we noticed that unlike ionic compounds, which is all the little circle packed together, there are some short lines connect the atoms, right? There are all kinds of lines connecting each other, which makes it a molecule. And the little lines between the atoms is called covalent bond. The covalent bond makes a molecule and makes it a compound. So that's why it is called covalent compounds. Okay, so the bond right here, the bond between the two atoms is called covalent bond, which is why they are called covalent compounds. So what's the difference between covalent compounds and ionic compounds? Ionic compounds is formed by ions packed closely together through ionic bonds. And for covalent compounds, 2 or more non-metal elements form a molecule by connecting with each other using covalent bonds. Covalent compounds we see every day, like water. 1 cup of water contains huge amounts of water molecules, which is also why the Avogadro number is so big. And here's a tip. The molecule doesn't pack closely like ions. On the contrary, the distance between 2 molecules is far. And this statement can also help us judging if one thing is covalent compounds or ionic compounds. How to tell whether it's covalent compounds or ionic compounds? In room temperature, ionic compounds are always solid. If it's a gas or liquid, it's covalent compound. Covalent compound can be gas, liquid, or solid, but in room temperature, ionic compounds can only be solid. So if it's a gas or liquid, it's no doubt covalent compound. Secondly, if you know this compound contains metal, it's ionic compound. And the third thing, if you can call it a blah 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 molecule, then this thing is covalent compound. We discussed that the distance between two molecules is far, so we can view them as individuals. But ions pack so closely, so we don't view them as individual. Neither we don't call them molecule. So if you call this compound a blah 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 molecule, it is a covalent compound. For example, you can say a water molecule, a carbon dioxide molecule, but you can't say sodium chloride molecule. So generally, if you can call one thing a molecule, then this thing is covalent compound. Any question here?
No.
Okay, that sounds good. So that's the class today. Thank you all.